Hello everybody. We are solving an example about the pseudo-steady-state molecular diffusion, and this example is about the diffusion of oxygen in silicon oxide. We have a reaction that takes place between oxygen and silicon, and this reaction is silicon plus oxygen produces silicon dioxide, and this silicon dioxide is formed on the surface of the silicon. As the reaction proceeds, more silicon oxide is formed, and the boundary on which the reaction takes place is moving downward. So this is what's happening. This is the why we call it a pseudo steady state, because in the very beginning we started with a whole thickness of silicon. As the reaction proceeds, more silicon oxide is formed on the surface, so oxygen has to diffuse through the silicon oxide to reach the surface of silicon to react and produce more silicon oxide, so silicon oxide layer gets thicker, and so on. We say that the diffusion of oxygen through silicon oxide film limits the oxidation process, which means that the formation of silicon oxide is limited by the oxygen diffusion. So the reaction is very fast compared to the diffusion, because once the oxygen is there, the silicon oxide is formed. So this is what this sentence means. And we need to develop a model to predict the thickness of silicon oxide layer as a function of time at this temperature. So I want to know how delta changes with time, or get delta as a function of time. And we know information about the silicon oxide thickness, density, which is density of this layer, and we know the molecular weight of silicon oxide. We know the molecular diffusion coefficients of oxygen in silicon oxide, and the maximum solubility of oxygen in silicon oxide, and the total pressure. So I know some like good number of information. And before we solve the problem, we have to list our assumptions. So the first assumption is that the oxidation takes place at the interface only, so we don't have any reaction during diffusion. This is the first thing. The second thing is that we said that oxygen diffuses from the top layer of silicon oxide until it reaches the interface between silicon and silicon oxide, and it's consumed there. So we have a steady state. There is a source for oxygen, and there is a sink for oxygen, and we assume that the oxygen in the gas phase is always available. So we have like a constant source of oxygen. And again, we mentioned this, that the reaction is very rapid and the concentration of molecular oxygen at the interface is 0. So this is the consequence of having a very quick reaction. And the flux is one-dimensional because we don't have any information about diffusion in X or Y dimensions, so it's only in Z direction. Z dimension, and that the rate of silicon oxide film formation is slow enough so that at a given film thickness delta there is no accumulation, which means that the assumption of pseudo steady state is valid. We have thickness of film increases with time, but the film formation is very slow, and this is a pseudo steady state process. We assume that the thickness of wafer does not change. So this means that this is a good point actually, that if we start with 3 millimeters of the silicon, for instance, and then we had a reaction that consumed 1 millimeter of silicon, formed silicon oxide. So this silicon oxide will have the same thickness of the original silicon. So the total thickness of this film is constant, because if we assume that the volume of silicon oxide is different from the volume of silicon, then this boundary is going to change as well. So we don't have only change in the boundary here. We have change in the two boundaries, which is going to make the pseudo steady state assumption is not a valid assumption. So this is an important assumption to make. And finally, we'll assume that the temperature is constant, so that we have constant diffusion coefficient. And then we can start the solution. So we'll start with the general equation, which is this, and then we get an expression for the flux. We have no diffusion of B because it's in the solid phase, it's unidirectional. And if we, and of course keep in mind that this is X, we have CA over C because it's a solid phase. We mentioned earlier that Y is only for gas phase, X is for liquid and solid phase. So this is what we're using here is CA divided by C. And here we can use the information that we know. So we have the maximum solubility of oxygen in silicon oxide, which is this. And this is 9.6 multiplied by 10 power minus 8 mole per centimeter cube, which is a very, very, very low concentration. The value of Ca divided by C would be even lower. And that's why we can assume that this term is very, very small. And we can assume that it is negligible, which is a valid assumption, but it's not just for the sake of simplification. It's a very, very valid assumption. So we can cancel this term and put the flux equation in this form, and we can integrate it. We know from this equation that flux is constant, so we can get the flux out of integration. It's gonna be from 0 to any delta. I'm not putting specific value, and we know at 0 C equals CAS, which is the maximum solubility of oxygen in the silicon oxide, which is the boundary condition. And here we have 0 because it's totally consumed. You can put it this way, or you can put it as boundary conditions. You integrate, you get the constants, and then substitute in the equation. They both will work. And then we can do the integration. We get the value of, or the form of the flux. So the equation tells us that the flux equals diffusion coefficient multiplied by the concentration at the surface divided by delta. And I encourage the like whoever is going through similar procedures to do quick checks on the equations to make sure that they are logical or not, they make sense or not. So for instance, here you see that the flux is directly proportional to diffusion coefficient, which is logical. It's directly proportional to the concentration at the surface, which is logical because as you have higher concentration, you have higher driving force. So this makes sense. And in the same time, you have the flux inversely proportional to the thickness because thicker layers would reduce the flux. So it's logical form of the equation. And then, so this is the first part. The second is to do balance equations on the interface. So when we do the balance equation on the interface, we would find that the molar flux of oxygen diffusion, which is what's going to the interface, equals the molar flux of SO if silicon oxide accumulation or the silicon oxide formation. So this is the balance equation. We have already calculated this from this equation. We have the flux, which is dC divided by delta, and now we need to get a form of this equation. So it's exactly the same as before. We have the flux of silicon accumulation is dN silicon divided by S. S is the cross-sectional area. Sometimes it's put at S and some because surface area, and sometimes it's A because it's area. But anyway, so this is the cross-sectional area. And the N equals the mass divided by molecular weight. Mass equals rho of silicon oxide multiplied by S multiplied by delta. And we can cancel the S in the numerator and the denominator and get the constants out of the integration. So this is dC divided by delta equals these constants, rho divided molecular weight multiplied by d delta by dt. Again, it's very simple integration. You can do the integration and then you will end up with this form of the equation. Okay, so we'll see that delta is directly proportional to square root of t. So t square will lead to 1 increase in delta, which I mean it's proportional to unit increase in delta. And you'd see all these constants we know the values of these constants. So we know molecular weight, we know diffusivity, the maximum concentration, we know the rho of silicon oxide, you know everything. But one more thing I would like to encourage you to do as a quick check is to make sure that the units are the units are homogeneous. So the thickness has the units of or the length, the units of length, which is centimeter for instance. So if I use the molecular weight as gram mole per gram per gram mole, and diffusion coefficient centimeter square per second, this is gram mole per centimeter cube, this is gram per centimeter cube, then you would see that the units of this constant term is going to be centimeter square per second. And if you multiply it by t, it's going to be centimeter square. Square root of centimeter square is centimeter. So now we have homogeneous units. So this is one check. It does not tell you that the equation is right, but it can tell you that the equation is not wrong from the units point of view. If there is a problem with the units, then the equation is not right. So this is one quick check that you can make. And by substituting with all these values, of course, you have to make sure that these are all in homogeneous units, so they're all in centimeter, this gram, and this is gram mole, and everything. And by substitution, we can see that the equation is square root of 1.37 multiplied by 10 power minus 14 multiplied by t. And this is a very, very, very small number. It's something multiplied by 10 power minus 7 multiplied by square root t, which means that it's a very, very small thickness with this when calculated from this equation. And one thing that we can do is to get the delta and get the change of delta with time, which is a useful parameter. It tells us how the film thickness increases with time. And if you plot them, you would see that the scale here is in microns, which is 10 power minus 6 of a meter. And you'd see that for this scale, we have the maximum value is 0.33, almost 32, something like this, micrometers, which is a very, very small thickness. And you would see that for this, even for this small thickness, it took 20 hours to reach this thickness. So it's a very extremely slow process. One thing that you would notice here is that it took us, or it takes the silicon oxide almost 5 hours to reach 16 or 0.16 microns, and it takes the silicon another 15 hours to increase other like the same thickness, to increase more 16 or 0.16 micrometers. So 5 hours are needed in the beginning to reach a thickness, and to double this thickness it takes us 3 times the time, which makes sense. This is something that we can predict from this from this equation, and this makes sense here to see this plot at the very beginning of the process, where there is no silicon oxide, or the thickness of silicon oxide is 0. There is no resistance to mass transfer. It's only silicon. So the change of thickness with time in the beginning was very quick, but as time goes, the silicon oxide gets formed, and then the change of thickness with time gets slower and slower and slower. And that's why we have this long time needed to increase the thickness of the silicon oxide layer. So this is one thing that we can use as a proof or a validation to our assumption that this is pseudo steady state. And as we see, it takes a lot of time for like a very, very small change in thickness. So this is the second type, which is the pseudo steady state. Next video, inshallah, we will talk about the equimolar counter diffusion, which is the second type of steady state molecular diffusion. So I'll see you then, inshallah. Goodbye.